Today we're going to talk about one of the first functions of many that we're going to talk about over the next couple lectures, but just a basic linear function and what I think we need to know for it going forward in this class. When we talk about a linear function, I'm just talking about a function with a constant rate of change. And that constant rate of change, I'm going to hit on down here when we talk about slope. Okay? All of your answers tonight, I'm going to want in this slope-intercept form that you have seen before, y equals mx plus b, where m is my slope. And this b down here, well, that's my y-intercept. So I guess it'd actually be the point 0b would be my y-intercept. Okay. So what do we remember from slope? I'm going to skip some slides, by the way, as I go through just some stuff that I want to skip at least this year. So slope. First thing that comes to people's minds when we talk about slope is that it's rise over run. I can count how much my slope goes up and then how much it goes over and get an equation for it. Well, also, what that means is if I'm counting how far it goes up, I can also just subtract off y values and then subtract off x values and then divide them. So I want to try just that first. Actually, I want to talk about whether or not we know something's increasing, decreasing, or constant. So if I have a line that is going up to the right, well, if I was to plug in 2 points on this line, plug it into my slope formula, I would get a number, and that number would probably be greater than 0. Anytime I get a slope that's greater than 0, it means that my graph is going up to the right. Whereas if I get a graph that's going down to the right, it's going to be decreasing because my slope will be negative. Well, I got positive, I got negative. What if I get a slope to be equal to exactly 0? Well, that must mean that it's a constant function, and it's just going straight to the right. It's not going up or down. So if I was to give you 2 points, hopefully you could find out what the slope is, and then judging by that, without even looking at the function, you're going to be able to tell whether it's an increasing, decreasing, or constant function. Okay. So I'm going to be using my slope formula, y2 minus y1 over x2 minus x1. I'm just going to plug this in. This is the x and y in my first point, and this is the x and y in my second point. So plugging in those points, I get -1 minus a -5. Careful on that. And then I have -7 minus 4. So I get -4/11 for my slope. Since it is negative, that means that it is a decreasing function. Let's try the same thing. I'm going to change up how I word it to you. It says the population of Dexter increased from 6,400 to 10,100 between 2008 and 2012. Obviously going to be a little bit fictional here. Find the change of population per year if we assume the change was constant. Okay? When it says find the change and we're dealing with linear functions, that's just a fancy way of saying find the slope. Find the slope. So if you need to, most of the time when we deal with these functions, my x's are going to be my years, and my y is going to be whatever's going on in the year. In this case, it's population. It might be how tall someone is. We're going to do here in just a little bit. So I can actually form points if you want to. So 2008, 6400, and then 2012, 10,100. And it's just asking the same thing the previous slide did. So I would do y2 minus my y1 over x2 minus my x1. And whenever I type all that in my calculator, I get 925. What does that mean? Just as the problem was asking, that on average, between the year 2008 and 2012, the population grew by 925 people each year. So let's talk about point slope form and what all applications we can have with it. Now the point slope form, it comes from my slope again. I'm going to go ahead and rewrite my slope. I'm going to multiply both sides by this denominator to clear it of fractions. And so since we're just talking about a point and a slope right here, there's no need for the ones and twos. So I'm going to get rid of these twos. I'm going to rearrange it as well. So I get y minus y1 equals m times x minus x1. And that is my point slope form that I want to use on these next problems. So I'm going to use this whenever I'm given a slope. Oops, I'm given a slope and I'm given a point. I'm just going to be a plug and chug and then try to get back into that original form. It says write the point slope form equation that has a line with slope of -1/2. Well, that tells me my m. That passes through the point 5, 3. Well, that's just my x1, x1 and y1. And then it wants me to go ahead and simplify that down to slope intercept form. So just using my slide, the equation I had on the last slide. Let's see. Plug in the m, the x1, and the y1. So I need to add 3 to both sides. I've got to get that y by itself. By the way, that answers the first question. This is my point slope form. So if I add 3 to both sides, I just get y equals, distribute this -1/2 plus 5/2 plus 3. I got some like terms to combine there. My constants on the end. 5/2 plus 3 gives me 11/2. And that would be the answer I want to end with. I'm going to change it up a little bit. I want you to work this one. Hit pause on the video, and then we'll see if our work matches up. Now, all we're given was 2 points on this. That shouldn't have been a problem. We should have plugged it into our slope formula to get 1/3. Now we have a slope. We have a couple points. I tend to choose the one that comes out a little bit smaller, plug it into point slope form, and I get my final answer of 1/3 x plus 4/3. Oops, all kinds of stuff going on here. All right. Now I like it when they want me to do a graph. Now I can definitely work this the same way if I'm not given a graph, or if I just want to use these 2 points. I could do m equals rise over run, y2 minus y1 over x2 minus x1, plug in one of those points. But man, it's just so easy if I'm given a graph to just go ahead and find the slope. Okay, you can even start from here. But I'm going to go ahead and start from dot to dot and go 1, 2, 3, 4, and I go over 6. So 4, 6, or 2/3. Remember, b is just going to be my y-intercept. I see it goes through at -2. So just plugging that in, I get 2/3 x minus 2. All right, Oscar the Grouch here. In 2000, Americans used approximately 380 billion plastic bags. In 2005, approximately 392 billion were used. I want to write a linear equation relating the years and the number of bags used. How many plastic bags are expected to be used in 2017? There's a couple ways to work this. A couple different answers I will accept on it. Again, remember, when we're talking about years, those tend to take up my x's. Now, since my years are so big, 2000, that's going to blow up my numbers. So what I'm going to do is I'm going to let this 2000 be x equals 0. That will represent the year 2000 when I plug in 0. So to find out my slope, it's going to work just like the last word problem we have, where I can write out 2 points. Let's see, my y2 would be this 392. I'm going to let the billion roll over to the units. And then I have 380. Okay. Now, right underneath this 392, I'm going to write the corresponding year. Now, if x is 0 for 2000, that means 2005 would be 5. So I get my slope to be just a simple 12/5. Once again, you have your slope. You actually have your y-intercept. Because if I count this as my y-intercept, I can just bring this over. Y equals my m x plus my b. My b is just my y value when x is 0. So it's 380 billion. If you use the 2000 and the 2005, that's perfectly fine. I will have that answer as well. So for the year 2017, trying to figure out how many trash bags were used, I don't want to plug in 2017. I just want to plug in 17 in for my x. Okay. So I do 12/5 times 17, add 380. It gives me 420.8, I do believe, billion bags. It'd be a lot of trash bags. Or plastic bags. I guess they could be those Walmart sacks as well. So the new breed of Oompa Loompas are being created in a lab in New Mexico. I wonder where those little dudes came from. The height of a random Oompa Loompa is recorded after the given days. Use the table to write a linear function where t is the number of days since the Oompa Loompa was genetically engineered. Now, for what we're going to be doing in my class, it might be different in some of your other classes, but I like to use the first and the last points. I assure you on this problem, it doesn't matter what 2 points you use, you will get the same answer. But later on in statistics, I tend to use this rule right here. So I want to go ahead and get you used to that right now. So finding out what the slope is, I actually get the slope to be 2 millimeters. So what that tells me is that the Oompa Loompa is growing on average 2 millimeters per day. I have all the points I need right here. All right, these are all XY points. They're just written in a table. So if I have a slope and I have a point, I'm going to choose this one right here that has the really easy 1 and 0 in it. I'm ready to plug this into my point slope form. And so y minus 0 is 0. Distribute the 2. And then this right here tells me the height of the Oompa Loompa after X number of days.